Hello APC Mechanics students, today we will solve the past paper FRQ Set 1 2022 Exercise 1. Then let's start. A block of mass M is pulled across a rough horizontal table. So because the table is rough, then we have friction. By string connected to a motor that is attached to the floor, the string passes over a pulley with negligible friction that is vertically aligned with the left edge of the table as shown. The string and pulley both have negligible mass. The pulley is at height h above the table. The motor exerts a constant force of tension Ft on the string. So the tension in the string, basically the motor is exerting a tension Ft on the string because because the pulley is massless and the string is inextensible, then here we would have also a tension force given by Ft. And the block remains in contact with the table at all times as the block slides across the table from axis equal to L to axis equal to 0. So basically the block will slide from this position into this position, taking into consideration that the positive direction is to the right. The coefficient of kinetic friction between the table and the block is mu k. Express all algebraic answers in terms of m, h, ft, x, mu, k, l, and physical constants is appropriate. This statement is super important. Now anything that will be derived, we need to double check that it's being expressed in terms of these. Now in part A, on the dot below that represents the block, draw and label the forces, not components, that act on the block when the block is at x is equal to L. Each force must be represented by distinct arrows starting on and pointing away from the dot. Now at this particular position, x is equal to L, what are the forces acting on the block? Mass, then we have the pull of gravity. Support, then we have the normal push. String, then we have tension. And there is tendency of motion to the left, then friction at this particular moment will be acting to the right. Alright, now here in this case the normal push should be represented in length to be smaller than the pull of gravity because there is a pulling force which is the tension force. Then let's represent the forces. So always take into consideration the relative length of the forces. Then let me say this is the pull of gravity, Fg. We have the normal push to be up, smaller in magnitude compared to Fg. We have the tension. Now it is not necessary at this stage to represent the angles, but it's better for us to put the angles because later we're gonna project. And we have the friction acting to the right. Now part B, derive an expression for the angle theta that the string makes with the horizontal as function of x. Now we need to determine the expression of the angle theta as function of x. Now we can utilize this triangle to be the point A and the point B and the point C. Now here I suppose they didn't mention that the block is at x is equal to L in part B, so we're assuming that this would be, so AC would be x in which the block is at any point between A and C. Alright, so this is h, this is x, and the hypotenuse would be given by radical h square plus x square. Now in order to determine theta, theta can be determined by referring to any trigonometric function. I would say sine theta. You can do it for cosine and for tangent. Sine theta is the opposite, which is h, divided by the hypotenuse, which is radical h square plus x square. Then here we can say that sine theta is given by h, which is radical h square, h over radical h square plus x square. But we need theta, not sine theta. In this case we can invert the function, then theta is given by the inverse function of h divided by radical h square plus x square. Indeed our expression has been expressed as function of x and appropriate constants, and one of them is h. Now this is it for part B. Let's go on to the next page. Derive an expression for the normal force exerted on the block by the table as function of the block's positions x. So here in this case, we need to determine the normal push. Then we can say that the forces are balanced along the vertical. So we can say that the pull of gravity would be balanced by the normal push plus the vertical component of the tension, which is given by sine theta. And in this case, the normal push can be isolated in order to find it in terms of the other forces. Then I would say that the pull of gravity is balanced by the normal push plus the tension force multiplied by sine theta, the vertical component. And the reason here, if you don't want to apply Newton's second law, you should write balanced forces, because there is no upward or downward motion, as have been mentioned in the text, that the block will remain in contact with the support. And we're searching for the normal push. Then the normal push in this case is given by the pull of gravity, which is mg minus ft sine theta. Now at this stage, we need to compare what is written here to what is required from us as an expression format. We need to have mh. We can use any of these. Now if you check, it is expressed in terms of m, fundamental constant. Ft, it's fine. If you check, we can express in terms of ft. However, theta should be replaced by x, and this can be done by referring to the previous part. In the previous part, we have determined that sine theta can be expressed as this. So now that would be equal to mg minus ft multiplied by h divided by radical x square plus h square. Then the expression of the normal push is given by this. Now derive an expression for the magnitude of the net horizontal force F net exerted on the block as function of the position x. Now this part is very tricky for several reasons, because we need to determine the net horizontal force, and not in particular the net horizontal force, but the magnitude. So let me start by writing the net horizontal force. Now what are the forces acting along the horizontal? We have the tension and we have the friction. Now here the tension, I will erase this. The positive x direction was given to the right, and so right is positive horizontal direction and left would be negative horizontal direction. Then if we're calculating F naught, this would be preceded by minus sign, and this would be preceded by a positive sign. Okay, and that would be Ft cosine theta. So here let me write that this is given by minus Ft cosine theta plus the friction. Now it is allowed to express in terms of Ft. I will keep it like that. We need to convert theta as function of the position, and this can be determined by referring again to the triangle, which is ABC, that we have utilized. So this is A, B, C. If we're talking about cosine theta would be the adjacent, which is basically x when m is at an intermediate position. So x divided by the Pythagorean sum, h square plus x square. Now what about friction? Independent of the state of motion, friction can be given by mu k multiplied by Fn. And now from the previous part we have the expression of Fn, so that would be equal to what? Minus Ft multiplied by x divided by radical h square plus x square plus mu k multiplied by Fn, which is basically mg minus Ft multiplied by h divided by radical x square plus h square Okay, now let me represent my solution more neatly. Now here what we can do, ft appears to be here and to be here, so I can factor minus ft out and open a bracket. We have x divided by radical h square plus x square plus mu k, which is the factor that's found here, multiplied by this one, h over radical x square plus h square plus mu k multiplied by mg. But remember, this is the net horizontal forces exerted on the block. We are interested in the magnitude. So basically, if this value is positive, then we're gonna keep it as it is. If this value is negative, we need to consider the opposite of this expression. How can we know whether this is positive or negative? We need to refer to the scene of the problem. In the scene, basically the block will be moving to the left, which means that the horizontal component of the tension in the negative direction is greater than the friction which is in the positive direction, which means that this overall is negative. Then this answer is wrong. Now I would say the magnitude of F naught would be equal to, so I will consider the opposite of this, which is Ft multiplied by x divided by radical h square plus x square plus mu k h divided by radical h square plus x square minus mu k mg. Alright, so that would be our answer. So pay attention whenever they're asking for the quantity itself or the magnitude of the quantity, especially whenever we're dealing with directions. Now in part D, write but do not solve an integral expression that could be used to solve the work. We know that the work is expressed as an integral to move from L to 0, so we are restricted to the direction of motion from L to 0, of which force done by the string, which means the tension, a dot product between the tension and the infinitesimal displacement. Now what does this represent? This is the projection of Ft along the x-axis. So in this case, the positive x-axis is given to the right, so we have a minus sign, Ft cosine theta. Then that would be minus integral from L to 0 Ft cosine theta multiplied by dx. Before I continue with this integral, let me refer to the previous two expressions and make sure that they have been expressed in terms of the constants as mentioned in the text. We are allowed to express in terms of m, fundamental constant, tension, and h, so that's fine. We are allowed to express in terms of the tension x, h, let me double check for mu, h, m, and g, and also I will double check for m. We're allowed to express in terms of m, perfect, and mu k, that's perfect. Now here, before I drag the tension out of the integral, I need to double check that the tension is constant, and this has been stated in the text. The motor exerts a constant force of tension T, so tension is constant, can be dragged out of the integral. Otherwise, if the tension is not constant, it cannot be dragged out. So minus Ft integral from L to 0. Now what is cosine theta? It has been determined to be x divided by radical h square plus x square, and we will stop here, and our answer would be given by W is minus Ft, the integral from L to 0, x divided by radical h square plus x square dx, simply because they mentioned in the question not to solve the integral. Okay, so they have mentioned in the text do not solve. Now in part E, does the string do more, less, or the same amount of work when the block moves from x is equal to L to x is equal to L over 2 compared to when the block moves from x is equal to L over 2 to x is equal to 0. So basically what's happening here, first of all, we have divided this segment into two, from L into L over 2 and from L to over 2 to 0. So basically this is stage 1, phase 1, and this is phase 2. For the two phases, the value of the displacement is the same because it has been equally divided. Now the work depends on what? It depends on three factors. It depends on the force, it depends on the displacement, and it depends on the angle. For both phases 1 and 2, the force is the same, so it doesn't play any role because the tension remains the same. The displacement is the same, so the displacement doesn't play any role. Now, however, if you imagine that the block becomes closer toward the origin, the angle theta increases, and the biggest proof on that, if it is aligned here, then the angle theta would be almost 90 degrees. Okay, so as the block moves from L to 0, the string opens more and the angle increases. And we know that whenever the angle increases, the work done by the force decreases, because we have mentioned previously throughout the course that as the force becomes more aligned toward the displacement, the theta, the angle with the horizontal or along the displacement, decreases, the work done by the force is greater, which means that the work done by the force in the first phase is greater than the work done by the force during the second phase, because in the first phase the tension is more aligned toward the displacement. So here, if we refer back to the question, so we will say they're telling us, does the string do more, less, or the same amount of work on the block as the block moves from x is equal to L to x is equal to 2 L over 2 compared to when the block moves from x is equal to L over 2 to x is equal to 0. So basically in the first phase it will be doing more work, and our reasoning would be, so we need to justify our answer. So usually they will give you specific mark for choosing the correct reasoning. Now we need to justify. Justification would have another mark. Then let me say, since when the block moves from x is equal to L to x is equal to L over 2, the angle theta is smaller for the same displacement or for the same value of Ft and for the same displacement, which makes the force more aligned along the displacement. Then the work done is greater. Then that's it for me in this video, guys. See you soon in a new one.